Hello and welcome to another video with Dr. G. Today we're talking about Batman's crime solving efficiency. And so Batman is here at his lab in the Batcave looking at a piece of evidence to try and solve another crime, right? So the question is, does Batman solve crimes faster than the average detective in Gotham? So we will want to compare how long it takes Batman to solve crimes to the established timeline of GCPD, right? So here is data collected for an entire year for the departments, and it is summarized below. So GCPD has a mean time, the population mean, mu, of 72 hours, and the GCPD standard deviation, the population standard deviation sigma, of 10 hours. Now we took a simple random sample of Batman's time to solve 10 recent cases, and we find this data here for the amount of time it takes him to solve. All right. So now we do have a couple of assumptions. Since the sample size is less than 30, we need the population to be reasonably normal. Given that the population of solving cases is normal, we can actually continue with the test. So we are now headed over to Excel to handle this very difficult case, right? So here we are in Excel. I actually added a column and pulled in the data. Most of the time, these four values are going to be given. That's why they are highlighted in yellow here. Now, the hypothesized mean would be how much time the average case takes for a GCPD. And so we're going to assume the null hypothesis that the mean time for Batman would be similar. Now, because we have the population standard deviation, it's 10, we are doing a z-test. So we're going to generate a test statistic z-score, and then we're going to use the normal distribution to solve it. And the reason we're doing that is because we met the two assumptions, right? That we know the population standard deviation and that the population is reasonably normal. Given those things, we need to do a z-test and use the normal distribution. Now, the sample size I know from over here is 10. If you did have data, you could use the count function and do that in A, and we can just count everything that has a number in column A using the colon, and that would give us a really nice start. And then the sample mean, now again, I do usually this is going to be the average is going to be given to you, but here we can just take the average and get 34.8. Now, in Excel, I do need to calculate the standard deviation, and so the standard error, I need to calculate the standard error. I take the population standard deviation and I divide it by the square root of the sample size. So 10 divided by the square root of 10 is approximately 3.16. Now my test statistic, right, is going to be my sample mean minus mu divided by the standard error. Now, I'm actually going to do the same thing for a t-test. It's just here we're going to use the normal distribution, so the test statistic is a z. But this is how you calculate the standard score, whether you're using a z-test or a t-test. Now, here we're going to do the normal standard deviation. I have a z-score. If I have a z-score, I might as well use the normal S distribution function, where the only input I need is the z-score, and then the cumulative is always going to be true. Now, this is a left tail test, which is exactly what we want. The p of x has got to be less than, so this matches our alternative test. So this is the one that we're going to use. And to 4 decimal places, it is 0. So obviously for this one, it's the complement rule. If you want greater than instead of less than, you would do 1 minus the less than, and that's going to give you the right tail. Now here is sort of the clever part. If you did have a two-tailed test, and I don't have a two-tailed test here, but if I did, what I put in was if D8, if my less than is less than 0.5, then do 2 times that D8, right? Do 2 times the left-hand tail. If it's less than 0.5, because remember, it's symmetric, right? The normal distribution is symmetric. So this is one tail, the left tail of the normal distribution. So for a 2-tail test, I do need to double the tails. But if this is over 0.5 and I double it, I get a probability greater than 1. So I don't want to do that. So if it is less than 0.5, use that one. And if it's not, then use the right tail, the upper tail, and double it. And that is how I get my 2-tail test. Now, obviously, this is less than 0.5. Even doubling it, it's still 0. And so that's very interesting. So now that I know that my p-value is basically 0, I can go back and look at the interpretation. So we're going to see that we reject the null hypothesis because our p-value is so small. So what we would say is at the 5% level of significance, right, we reject that the mean time for Batman to solve a case is 72 hours. We have confidence that the mean time for Batman to solve a case is less than 72 hours, and that p-value is less than 0.001. Now, we don't normally put p-value is equal to 0, so if it was 0 to 4 decimal places, this is the inequality that we would put. Now, what does this mean in practical terms? It means that Batman solves cases on average in less time than the GCPD. And that is what we are rejecting, is that his mean time is the same as the GCPDs. If you got anything out of this video, if you learned a little bit more about Excel, then that makes me happy.